Hello again, and welcome back to chapter 3 now for the Psych of Aging course. Attention is where we are at next. I have it labeled here as attention and executive function. I'm going to unpack as we go through the notes here on what exactly we mean by that. The main theme will be about attention, but executive function will have some relevance here as well. So let's get into that. We're going to start with two kinds of attention here, selective attention and divided attention. I have them both listed here. I'll talk kind of about both. Actually, I have many kinds of attention, maybe described on this slide, a little all over the place, but let's get started with the classic idea. How do we think of attention as working in the first place, right? We need a little bit of background in cognitive psychology, perhaps. And if you've never had a cognitive psych course or not yet, maybe you haven't been exposed to some of these ideas. So one classic idea for thinking about attention is this concept of the attentional filter. So let's think about what this means. Um, in an actual filter, right, like you're filtering water because it's contaminated or something, right? The goal here is to block the things that we don't want, right? Whatever the contaminant is, and let through only the things that we do want, which would be nice, clean water, right? And so we can take that analogy straight to attention, right? When we are always sort of operating in some sort of what we'll call a noisy environment. And by noise, I don't just mean auditory noise. Of course, that can be quite common. You can be in a crowded building, lots like the a lobby of some building with lots of people coming and going and lots of noise, people talking, or walking down the street in the city and there's car noise and all this other stuff going on. But noise, in a psychological sense, refers to things that are not relevant to the task at hand. And so we can have visual noise too, right? And that means a visually busy environment. One way to think about this, for example, is imagine when you're driving and you're stopped at an intersection and your plan here is to maybe make a right-hand turn. So you need to look left and make sure that the road is clear, right? That maybe there's cars coming, but they're really far down the road. And so you judge that you have enough time to pull out and make your right-hand turn, or maybe there's no one coming at all and the road's clear. But on the other hand, there's a lot of other stuff that to see when you look to the left. There could be buildings, trees, signs, pedestrians, lots of other things are there that might you could look at, of course, but they're not really relevant to making this judgment about making your turn. So therefore, those would be considered visual noise, right? You need to ignore all of that and pay attention to the presence or absence of cars coming down the road, right? That's visual noise. And so this can work for all of our senses. So the idea here is that when it comes to selective attention, I am attending to my environment. I am scanning my environment and I am looking for and trying to select things that are relevant to whatever task I'm trying to perform. So when I'm driving, my selective attention is focusing on driving related items of interest, whether they are visual signals, largely it is, right? I'm watching for other cars, but just driving down the road, I'm also watching for signs, stop signs, and so forth, or stop lights. And I'm also checking what's happening inside of my car, right? I'm looking at the dashboard, I'm looking at my mirrors, and so on and so forth. So we can tune out the background and only focus on our things that are really relevant to what we're trying to do right now, right? So that's what we mean by this filter. And what I've just described are pretty much all examples of what we can call top-down influences. And what this refers to, in the case of attention, bottom-up and top-down, this is like a metaphorical description of our cognitive systems where the top of the system is usually where we think knowledge and goals and plans and so forth are all stored. And the bottom of the system is the incoming sensory data. And so where I am attending and what I'm attending to in my environment can be driven by knowledge and driven by goals and plans. And that's a top-down influence, right? So, like I said, when I'm driving and I'm trying to pull out onto a street and make a right-hand turn, my goal, my task is to safely do that without pulling out in front of someone and causing an accident. So I have now knowledge and expectations about where I should be looking and what I should be looking for when making the turn, right? I know I have to look to the left, and I know that I have to look for a car or maybe even someone on a bicycle or someone else that might be coming that direction as well. And make sure that I don't hit them when I pull out, right? So those are top-down influences. But on the other hand, bottom-up influences can happen all the time as well. So, for example, if I'm driving along, sometimes they can be not very helpful, right? If I'm driving along, and you may have seen like a lot of billboards these days are not just static images, but they might actually have a digital screen that can flash bright colors and images, right, as part of a very evocative advertisement. And what is it designed for? It's designed to get your attention. Obviously, that's what advertisements are all about, though it's not exactly something useful when you're driving and you're trying to pay attention to what you're supposed to do, right, which is drive safely and look at the other cars. Um, so that's what we'll call a salient stimulus, right? It's very, very bright. It's visually loud. And we will also say it's um, uh, conspicuous, right? And so conspicuity is something that can be relevant to these bottom-up influences, things that really just pop out and stand out and capture your attention is the phrase. The concept of attentional capture is exactly that, right? That you're just kind of going along minding your own business, but something really noticeable and conspicuous happens and it just captures your attention. You're just like, whoa, I'm going to look at that, right? Sometimes it's good, right? Like in the case of um, maybe if you're driving along and a pedestrian runs out into the middle of the street, you're not really looking for that per se. You weren't expecting that to happen, so it's not likely to be a top-down thing. But if that person was wearing bright colors, especially, then that might just capture your attention, and you're going to go, "Oh no, I got to stop." And so the bottom-up information, in this case, captured your attention and allows you to safely avoid an accident. But like I also said, sometimes these are task irrelevant. They are distractors, right? They're part of that background noise that are not really going to always be helpful for a task. That's just everyday attention, right? Everyday selective attention is just about making sure we pay attention to the things we need to do. Older adults sometimes have less effective selective attention. And so what does that mean? Well, one way to think about it here is now I have the leaky filter analogy. And so in this case, leaky filter means, as I go back to my original analogy with filtering water, we're letting something through that we don't want to come through, right? So that could, go back to our driving example. That could be that situation where looking to the left to look for cars coming down the road, but there's something else there to see, a sign, right? Or whatever it might be, that normally we would have no difficulty ignoring and blocking that out and inhibiting our attention from ever looking at that. Suddenly, then we might find ourselves kind of captured by that kind of a stimulus, which now makes us at risk for making a mistake, right? Because now we spend too much time looking at something we really shouldn't be looking at, and now problems might happen. So this leaky filter suggests then that what older adults are experiencing here with attentional concerns is this idea of inhibiting distractors and distraction itself, right? So that would also imply that bottom-up influences work quite normally, right? Things can still capture our attention, things that are conspicuous and salient, like I said, all of those things are still happening normally. It's a attentional capture is well preserved, as I've written it here. But the point here is that it can be maladaptive, right? There are many situations where we can inhibit those kinds of distracting things, and that's where some older adults might be struggling. There's a few other kind of cases where we want to talk about with attention. So another form of attention is, we might call it an attentional set. So in this case, sustained attention, right? So what are we doing? Let's go back to the driving example. Let's say I'm on a long road trip, um, and you're just on a highway. Let's say it's dark, so there's not even very much traffic, so there's not much going on. You have what you see in front of you, right? You see the roadway and you see the lines on the road, and you've got your car and you're trying to maintain your speed and you're trying to maintain your lane position, and there really isn't much else going on, right? Low traffic, not much else to look at because it's dark. So that means you have to, your selective attention isn't really being challenged very much here, right? There's very few things to have to worry about as a distractor or anything like that. But you still have to sustain your attention. You've selected the appropriate thing, right? The position of your car in the lane and your speed. And you just have to maintain this, right? Or sustain this, right? So you're maintaining or sustaining your attention for a long period of time, right? You could be doing this for an hour or 2 hours or however long this long drive you have to make is. And so we'll call that vigilance as an everyday term, right? Just this long-term looking out for something, right? And vigilance is important because not only do I have to make small corrections here and there, right? Your car might drift a little bit in the lane, so you have to make sure that you notice when this occurs and correctly steer back. Or your speed maintenance might waver a little bit. You might find yourself speeding up without realizing it or slowing down. And again, you make small adjustments to the gas pedal, and this is what you're doing. But also, other things happen. So maybe there is an occasional surprise, right? That there's a pothole in the roadway, a sign telling you that there's an exit coming that you really need, right? Maybe you're going to miss that exit because you didn't look at that sign, right? So in these situations, right, you have to maintain your attention for long periods of time, but still also be able to respond to occasional, unexpected, and unpredictable kinds of stimuli. And so again, we're going to see performances decline here. This is commonly referred to as the vigilance decrement, right? Performance declines over time. Got another slide on that a little bit later on, but we're going to see again, that's another area of decline. We also want to talk about the narrowing of the attentional window. So what in the world is that? Well, again, I have a little bit more detail later in the slides, but we want to think of the attentional window. Um, let's use a different metaphor for right now. Let's call it the attentional spotlight, because that's another way to think about this, right? When I'm scanning my environment and I'm looking around, it's like I'm shining a little spotlight on things and I'm like looking at it and saying, is that something of interest? No. Okay, then I'm going to move to something else, right? And we're doing that. And it's one thing if that spotlight is really large, right? And I can really take in a lot of information and make sense out of it and make decisions with it. But if that gets smaller and smaller and smaller, that makes it a little harder for me to scan my environment and see potentially every single thing I want to see. So we'll talk about that as well. And then I mentioned divided attention at the top of the slide here. So this is what we want to think of as multitasking, right? In a multitasking situation, it's not just about trying to find that one thing that I'm trying to pay attention to, right? Like I said, with the pulling out onto a roadway, that's a single task, right? I want to turn right. I need to look for something coming from my left, and there's only one thing I'm looking for, which is the car coming down the road, and I can determine if it's there or not there, and then I can make my decision to turn right. But in a divided attention task or a multitasking situation, that is now doubled, tripled, quadrupled, right? How many different things do we need to pay attention to all at the same time? I have a note here to consider driving as well, because in a technical sense, in a lot of situations, think about driving around town, right? um, you're multitasking because if you're on, like I'm imagining driving across Orlando here on 408, you got a lot of lanes. You have to worry about maintaining your speed. You have to worry about maintaining your lanes, but you also have to worry about lots of other cars that are weaving in and out and going different speeds, and you're going to have to make continuous adjustments about what the behavior of the other cars are. You have to maintain your attention on where the tolls are and where your exit is. And not to mention when you're driving, you're also maybe paying attention to other things like any messages that come to you from your in-car displays, right? You're going to have your speedometer, your gas gauge, warning lights that might come on suddenly, right? Not to mention you might be listening to music or, like we're not supposed to. People have their phones out and they're scrolling on something, texting, talking, and these are all additional stimuli and additional tasks. And one of the things that's important when we talk about divided attention is the concept of attentional switching, because what we're not really doing is simultaneously doing all of those things at once. Rather, we can only pay attention to one thing at a time. So I can attend to my lane maintenance for a moment, but if I'm trying to do something else, then I have to shift my attention to looking at my dashboard display. And then I have to shift my attention to my phone. And then I have to shift my attention to my speed maintenance and then to my mirror. So we're always doing this kind of switching from one stimulus to another and from one task to another, right? And so driving is itself an inherently a divided attention kind of a task. When you add any of these other kinds of things like in-car technologies and touchscreens and phones, and it becomes an even more complex divided attention task. We're going to see some declines then for older adults when it comes to this ability to efficiently switch our attention between tasks like that. Again, a little more detail coming up. Let's talk about one example here. I mentioned on the title slide executive function. And one way to think about executive function is that it plays an important role in the concept of inhibition. And I mentioned this with inhibiting distractors, right? And so that's part of it, is that part of it, part of our attentional filter is inhibiting the distractors, and that's what we call the role of the executive functioning in the brain. So you might hear that term come up a lot when you hear about people talking about ADHD as an impairment of executive functioning, because it might be that in this case, because of attentional deficits, um, people with ADHD might also have trouble inhibiting distractors and not attending to distractors and separating task relevant information from task irrelevant information like that. But here's another way to think about inhibitory control. This is a classic, 100-year-old kind of demonstration in psychology that reveals um, what happens when we have maybe sometimes two competing tasks and two competing impulses to do things. And what happens is that we have to inhibit one so we can do the other. So on the left-hand side of this image, you just see a list of colors, color names, but also written in color, right? Green, yellow, red, green. And the task, of course, is to name the color, not to read the word. So when I say green, yellow, red, green, I'm naming the color of the ink, not reading the word. But that's okay on the left-hand side because that's the congruent condition when the color word and the color ink are the same. They're congruent with each other. And I can perform this task very, very quickly. But on the right-hand side is the incongruent version, in which, again, I have to say green, yellow, red, black, uh, red, green. I got confused for a second because, of course, it is harder to inhibit. What do I have to do? I have to inhibit reading, right? So it might be tempting to just read the words red, yellow, black, but that's not my task. I'm supposed to name the color. So I'm really supposed to say green, yellow, red, black, red, green. And that's harder when I'm looking down the right-hand side here. So we see that reaction times decline. Why does the reaction time decline? Reaction time is how long it takes me to actually get through the list, right? Let's not call it reaction time. Let's just call it task time. Um, and the idea is that I have two competing impulses, right? One thing that is a well-learned task is reading words, right? That's just like an automatic thing that we do, is we just see a word and we read it, because if we're already a well-learned reader, then reading words automatically is something that we just do, right? But we have to inhibit that automatic impulse because I know that my task is not to read the word, it's to name the color. So I have to inhibit one response and make sure I'm attending to something else, right? Don't attend to the letters, attend to the color, right? And this is an example of inhibitory control because people can successfully perform this task, that means that they can successfully inhibit the task irrelevant part of our cognition, but it does take a little bit of effort and a little bit of time, right? So we would expect quite naturally that older adults would show maybe an even larger decline on the incongruent version of the Stroop effect here. By the way, it's called the Stroop effect, named after the person who invented it. I don't remember their first name, but their last name was Stroop, and it was back in like 1925, I think, that this was first reported. Okay, so let's talk about the vigilance task next here. So what's going on is, again, we're going to sustain attention for a long period of time. And I use the example of being on a long road trip where you're just going to monitor certain things and maybe occasionally respond to something surprising. Now, it's difficult to do this in the laboratory. So what we have in the laboratory here, you can kind of maybe get an idea of what this task is like. So what's happening is that we have a screen, right? You're looking at a computer screen. It's just a bunch of dots, right? And so that's what you see kind of magnified there in the center here is just a big computer screen with lots of tiny little dots all over it. And every now and then, well, most of the time, nothing's happening, right? So that's what we're seeing here is 40 milliseconds, 1,000 milliseconds, 40 milliseconds, 1,000 milliseconds. So for those 1,000 milliseconds, which is 10 seconds, by the way, um, nothing is happening. It's you're just looking at a screen of dots. But every now and then, for 40 seconds, 40 milliseconds, so just a fraction of a second, something might happen. And we're looking at a something right here in this blown up version here, which is that a small, very faint, very difficult to see letter O has been presented. And that's our target. So when the letter O appears, my task is to press a button, probably just sitting there with the keyboard and you press the space bar, right? Um, that's the task. That's it. Not hard. Um, Except sometimes a distractor appears. The distractors are usually a letter D or a backwards letter D. So that way it's kind of approximately shaped like the O, but it's not the whole thing. And so your task here is to ignore them, right? Those are irrelevant. So if it's a non-target, then just completely ignore that. But when the O happens, press the button, right? And this is happening where the targets are occurring. Sometimes randomly here it's written as, every 1,000 milliseconds, there's something going to happen, but sometimes you can set this to randomize that. But importantly, the actual targets appear only a minority of times, right? Most of the things that are happening are actually just non-targets that you're supposed to just sit there and do nothing. And that's the task, right? This is a really boring kind of psychology experiment to have to participate in because you're just sitting here staring at a screen for 15 minutes, 20 minutes, 30 minutes, 45 minutes, an hour, even in some cases. We will ask participants to sit at a screen for an hour staring at dots while nothing is happening other than these D's, right? And you have to do nothing. But when the O appears, you're going to have to respond. And so our question is first, do you detect it, right? Did you correctly see that it was there and press the button, or did you miss it, right? So in the language of attentional research, these are called hits and misses, right? So a hit is when you saw the target and you pushed the button and responded correctly. A miss is when the target appears and you didn't respond to it. So you probably had what's called an attentional lapse, right? Your mind was elsewhere, even if your eyes were kind of glazed over looking at the screen. Your mind was probably elsewhere, and you didn't really attend to the task. By the way, if you've encountered some neuroscience on these kinds of topics, you might have heard of something called the default mode network. And that's the kind of thing that happens in the brain when we get bored. So your mind elsewhere, meaning that now you're thinking about things internally, right? You're reflecting on yourself, your memories, what you got to do later, anything else that's on your mind. And it's not task relevant. So what we'll call the task positive network would be whatever sensory regions are important for detecting this letter O. And that gets fatigued and our mind wanders, and then the default mode network takes over and we get bored and we have these attentional lapses. So that's one way to think about the vigilance decrement is that we see an increased miss rate here. But even sometimes the reaction time when people do show a hit and they correctly respond, their time to respond to that might be a little slower too. So that's two ways to think about the vigilance decrement here, right? Is we're going to have more misses and fewer hits, and we're going to have slower reaction times when we do show a hit. There might also be false alarms, which is when you press the button to the non-target. So again, that's another kind of error that shows up in the vigilance decrement is doing something when you're not supposed to do something. That means you've failed to inhibit that distractor, right? And you responded to it. Here's another case where we want to talk about the attentional window here. So this effect is called visual crowding. Uh, on the left is a kind of a classic laboratory example. So your task here is to keep your eyes fixed on the green dot. Just ignore the photograph of the road on the right-hand side and just imagine what's happening on the left here. And what's going to happen, I know this is not quite well demonstrated on the screen here, is that most of the time you're just staring at the green dot with an otherwise white screen in the background. But every now and then something's going to happen. You might see a letter randomly appear on either the left side of the screen or the right side of the screen. And you're not supposed to look at it. You're supposed to keep your eyes fixed right there on that green dot in the middle. When that letter appears all alone, like it does on the left-hand side, your task is to name it. I saw the letter A, perhaps, right? And it only appears for a fraction of a second, right? But what you see on the right-hand side is that the letter A is presented along with a bunch of other distracting kinds of lines in different orientations. And it's really hard to recognize the letter A here. And this is called the visual crowding effect, right? All of these little lines are all clumped and crowded together, makes recognition much, much harder. The image on the right kind of shows us what this could look like in a real life situation where on the left, if there's a pedestrian, a child is playing on the side of the road like they're not supposed to, uh, probably is very easy for us to see that, right? So there's an attentional capture probably happening there, like, okay, yeah, be careful and slow down. But on the right-hand side, the visual crowding effect might cause us to fail to recognize the potential risk here because of all of this other clutter on the side of the road. This is what might make construction zones dangerous potentially, right? Because now you're going to have maybe not children playing, but you have the actual people working on the roadway. But you also have signs and cones and lights and machinery. There's a lot of stuff over there, and your ability to detect the possibility that someone's about to walk out into the roadway or maybe get too close to your lane. Again, the visual crowding effect can influence this. So we'll call this the attentional window because our ability to extract this information from our periphery is impacted by the crowding effect, right? So your eyes are always fixed at that central location, and these stimuli are happening off to the sides. And so let's, like I said before, how wide is that spotlight of attention? And as it starts to narrow, then you're going to have some increasing challenges with these kinds of visual crowding effects. Another way to think about the attentional window is this kind of very famous study that's been around for about 25 years, give or take, called the UFOV test. UFOV stands for the useful field of view, and it's the same idea, right? How large is your attentional window, and does it shrink? So here's your task here, a little bit on the right. You're supposed to keep your eyes fixed at the center of the screen. Most of the time, there's nothing there, but every now and then something shows up, like a little picture of a car here, right? And then now that you know that this is your target, what's going to happen is that one of the triangles in these peripheral, you see these are like concentric circles made of triangles here. There's the inner circle right around that central car, and then there's the second one out, and then there's the third one further out, right? One of those triangles is going to randomly turn into something else. It's going to be another image. And if it's an exact match to the object in the center of the screen, you push a button that says, okay, I detected a match. If it is not a match, if it's something else, you do nothing. It's like the vigilance task. If it's a distractor, if it's a non-target, you don't respond. But what we're seeing here is that in this case, it is a match, so you should press the button, but it's happening in that outer ring of triangles, right? So what we see is that when we do this kind of study with young adults versus older adults, young adults do pretty well on this. Doesn't matter whether that target stimulus occurs in the inner ring, the second ring, or the third ring, right? They do pretty well across the board here. But what we see older adults is that they struggle when the targets are in that outer ring, right? They do pretty well. In fact, pretty much identical to younger adults when the target appears in that internal ring closest to the middle, right? It's when we hit the outer ring that we start to see the performance decline. And this is again suggesting that what we have discovered here is a narrowing of this intent of attentional window, right? It's a good way to measure this decrement, right? And we can see that happening with older adults. But one cool thing from the UFOV research is that if you have people perform this task for long periods of time, again, it's another one of those kinds of boring things like a vigilance task. So it's not exactly very exciting to do this for an hour at a time. But what we do find is that the longer you have people performing the task, the better they get at it, right? And this would suggest then that if I can take an older adult who's showing a decrement on the UFOV test, I train them on it for maybe a few months, right? Just have them spend an hour every other day or every day even for a couple of months until they get so much better at it that suddenly their performance looks a whole lot like the younger adults. But the big question, the real question is, does this generalize? This is one of those important things in all of psychology research related to what's called transfer of training. Usually we can find what's called near transfer. Near transfer is that when I train on one task, the skills that I have acquired will only generalize to other tasks that are very, very similar. Far transfer is when I have acquired a much broader kind of skill that would transfer to other tasks that are not functionally identical to the task I trained on. So what we would ask here is this just a task that where I'm just getting better at this thing, this game that I'm playing, if we want to consider this something like a game, or does this actually improve my real attentional window in the real world? So that way, anytime I'm engaged in any task that involves the attentional window, I will show improvements as a result. And that's exactly what the UFOV researchers found here, is that they measured older adults' driving skills before and after the UFOV training. And they find improvements on a lot of things like what I talked about earlier about these dangerous maneuvers called gap acceptance, right? Gap acceptance is the official term for what I described as pulling out of an intersection to make a turn because I'm waiting for certain cars to pass and I see there's a gap between the car that's passing me and the next car that's coming, and I have to determine whether that gap is enough for me to safely pull out and get up to speed. I have to determine the distance and also the speed of the cars. That all influences my gap acceptance. And stuff like this is could be improved with the UFOV training. So again, we're going to see that, okay, attentional windows are declining as we get older, but it's not exactly something permanent either, right? So maybe some possible training here to ameliorate these declines. Next up is divided attention. As I defined earlier, we can call this multitasking, but the term multitasking is usually not preferred within cognitive research because it gives the false impression that we're doing many things at the same time when it's really more about attentional switching, right? It's about attending to one stimulus related to one task, and then I have to shift over to another task and attend to anything relevant to that task, respond as needed, and shift again, right? So we're going to see then that there's lots of different stimuli. This is a good example of what's called serial processing. So another cognitive psych terminology here, if you've never had cog psych. Serial and parallel processing are two ways in which brains can process information. If we were capable of parallel processing in this context, we would sort of be like a super attentive person, right? But people are not really parallel processors for these kinds of things that we're describing here. We'll explain what parallel processing is separately, maybe. So serial means doing one thing at a time, right? Serial means in sequence or series. So that's exactly what I just described. I attend to one thing, one task, and then I do another thing. And I have to go in some order, in some sequence. And one of the things that's a big limit here is not just how much time it takes me to shift from task to task to task, but also I have to remember all of the different tasks that I'm trying to perform here. And this is where we also need to invoke working memory. This is going to actually come up in the next chapter a little bit more, but I want to mention it here because a divided attention task is about selective attention and attentional switching, but it's also about a working memory demand of remembering all of the different tasks that I'm trying to perform at this time. With driving, it's usually pretty well practiced, so I can remember to attend to my mirrors and to the road in front of me and to my instrument display and so on and so forth. But maybe for a new driver, it becomes a bigger working memory load and it's harder to remember, and maybe we forget and get and miss something, right? So um, that's what serial processing is. Parallel processing means you're doing many things all simultaneously, right? And you're processing things uh, all at the same time. And so the concept of parallel here means that you can have several processing streams all happening at the same time in the brain. This does happen for certain kinds of stimuli, um, but I think for our purposes here, maybe we don't need to get too much into the weeds on some examples of parallel processing. In the real world kinds of situations we're talking about here, these are pretty much all serial tasks, right? One thing after another in sequences. Now, what we want to do next here is we want to get a grip on what's actually happening in the brains of older adults that cause some of these known declines, right? So we've talked about failure to inhibit distractors, failures to inhibit impulses like in the Stroop test. We've talked about the attentional decrement, the vigilance decrement, and we've talked about challenges with shifting attention. And so we want to understand and the narrowing of the attentional window, right? So can we have some understanding of what might be going on here? We need some attentional theory, some cognitive theories, and maybe some neuroscience theories to help us out to understand all this process. So one way to think about uh, these attentional processes is the first theory is one of the oldest ones, where researchers here, Schifrin and Snyder, have identified um, two kinds of processes, right? Automatic and controlled. So an automatic process is actually defined here as a parallel process in some cases, but it's fast, importantly, and is defined as having low attentional demand and is something that's not necessarily prone to distraction. Going back to the Stroop test, reading the words is an automatic process, right? When I just see a word because I've learned how to read, right? Reading has itself become automatic for me. So therefore, when I see a word, I automatically read it, right? I can't stop my eyes from in my brain from seeing and reading the word itself. So in a way, we'll say that these automatic processes are also things that we might call mandatory, right? I cannot tell my brain to stop reading words on the screen in front of me, even if I don't say them out loud, right? That's the inhibitory part. Like in the Stroop test, we actually do read the word, but then I have to tell myself, but don't say anything, right? Don't name that out loud. I have to look at the color of the letters, right? And that's a controlled process, right? Controlled processes now happen much more slowly, one at a time. Oh, and by the way, why is it a parallel automatic process is parallel? Because when you look at a word, you don't really read it letter by letter by letter. You kind of see the whole thing and process all those letters at the same time. That's a parallel process, right? Anyway, let's get to the controlled process here. Slow, serial, and controlled. It requires effort, right? So I have to initiate some kind of internal control. That's where the executive function business comes in here, because like in the Stroop test, I have to initiate the conscious decision. Don't read the letters, name the color of the ink, right? And so this requires more cognitive effort, more attentional demand, we'll call it. And of course, we might also suggest here that it's more sensitive to distraction. So that's true in driving, right? Driving already is this task that is very controlled. It requires me to have to shift from one thing to another in sequence. And if you add in something else that distracts me, then I lose where I am in my sequence of shifting from one thing to another. Um, we would imagine perhaps that one simple experiment we could do. Let's imagine this, right? Let's do the Stroop experiment. But let's imagine that what I'm going to do in the Stroop experiment is I'm going to play maybe some loud music or have some bright flashing lights happening in the background while the person is trying to do the task. And what we might find is that in the congruent task, the effect of all of that background stuff happening is probably minimal. People will still be able to just go through that list pretty quickly in the congruent condition. In the incongruent condition, we're going to expect a decline in performance relative to the congruent. But if we add in a whole bunch of extra, you know, sounds and lights and all kinds of stuff flashing in the background, I bet we would expect to see an even greater decrement in the incongruent case in that case, because again, this is just adding to the attentional demand of an already demanding task, right? And so it's infiltrating that task and disrupting that task. I'm quite sure that that's probably been done. You might want to check it out, right? Go to Google Scholar and see if anyone's ever done an experiment like that and see what they found. And if no one's ever done anything like that, that would probably be a cool study to do. Maybe make it an honors thesis or something. I don't know. Okay, that's one idea. There we go. Inhibitory deficit hypothesis. So this is kind of directly related to the idea of inhibiting distractors. This concept goes back to the 80s, where what we're talking about here is simply reduced ability to inhibit the distractors. And one of the things that's happening here is that when this happens, if I'm not inhibiting these distractors, that means more information is coming into working memory. And this is kind of an important thing here that I didn't mention much at the beginning. Maybe I could have. What's the reason why we have this attentional filter in the first place, right? Why is it that we need to filter out the background noise and only let something else in? Well, obviously, some of that's just related to task relevance, right? If all of that background stuff is not relevant to whatever task I'm performing, then I don't need it. But more critically, we want to think about the fact that our working memory systems are, we usually think of them as capacity limited, right? You've probably heard the concept of 7 plus or minus 2. That's a problematic concept. Again, we'll talk about that in the next chapter a little bit. But it's at least useful for understanding that we do have this kind of storage limit in our working memory. We can only fit so much in there, right? So that means I don't want to overload it with irrelevant information. I want to make sure that I'm only letting in task relevant information, inhibiting everything else, because if any of that extra stuff makes it in, it's going to overload my already limited working memory systems, and that's going to, again, cause error, right? We don't want that. So that's another way to kind of theoretically understand what's happening here. Another comes from Wickens here. That's in the top right. It says Wickens' model of human information processing. So we got a little stages of information processing there. We don't necessarily need to worry about every single one, like say the sensory store. But we get information in from our senses, so there's perception, sensation, and perception there. And then attention determines which information is allowed to go further into our minds, right? So some of that makes it into working memory. And then from there, we use working memory to make decisions and select responses. Some of that information in working memory also gets stored in long-term memory. And then once we have made decisions and selected a response, we have to execute the response. And that generates new information and it loops back, right? What Wickens is showing here, though, is this little bubble at the top labeled attention resources. And it looks like a little fuel tank, right? It's full of some kind of a liquid. And the arrows are pointing to perception, working memory, decision and response selection, and response execution as boxes in the flow of information processing that might be using these resources. So we can think of it, if we want to, as like an actual gas tank in the car that sends fuel to the engine. But in the human information processing system, we have lots of engines that need some fuel, right? And as each one of these gets maybe more loaded with information, so if I'm in a perceptually demanding environment, that perception box is going to use some of these attentional resources. If my working memory is heavily overloaded with a lot of things I'm trying to remember, then the working memory box is going to get loaded up with those attentional resources. And likewise for decision making and so on and so forth, or if I'm performing a very complex task that requires a lot of attention going to what my hands are doing, the response execution box might get those resources. What's important about the theory is that we only have a finite amount of these resources, and when the tank runs low, that's it. So something might have to get sacrificed, right? So if I'm running out of resources, uh, then maybe I can't process all of that perceptual information, or maybe my working memory starts to flag a little bit, and I start forgetting things, or my decision making is not as effective as it was, and so I make some bad choices and bad decisions because of that decline in my resources. So in this case, I obviously want to preserve the resources, right? We can also now imagine, for example, what happens with vigilance is that maybe over time, we talk about resources being depleted while we're engaged in a task, but obviously that's not permanent. We can potentially somehow regenerate these resources so that we can do more stuff later on. But when we are engaged in a kind of a sustained vigilance task where we don't have a chance to take a break and rest from that, like when you're driving, you can't just mentally tune off for 15 minutes. You could maybe stop, right? If you could pull over at a rest stop and give yourself that mental break, that's useful for restoration of these resources. But the rest of the time, you have to persevere, right? And so when the resources are depleted, maybe that's what was happening with the vigilance decrement, perhaps, right? So now we might say that another way to theoretically think about aging is that maybe the resources are reduced in some way. Maybe there's just fewer resources to go around altogether, or maybe the ability to allocate them effectively across the boxes might also decline, right? We see here we have to allocate here to these different boxes. Another way to think about it is that maybe it takes longer to restore them, right? So after they are depleted, we want to take a break and regenerate them, but maybe that is not happening as efficiently as it otherwise would. What in the world are these resources? This is a kind of a thorn in the side of many cognitive psychologists. It's not a well-defined concept, but we might simply just want to think of it in some cases as the metabolic resources to the brain, right? Glucose, blood supply, giving energy to neurons, and neurons become fatigued and then they need to recover. And so that could be at the physiological level what's really happening here. But a lot of times we don't really concern ourselves too much with those questions. One thing that we also know for older adults is that even though we show some laboratory declines in a lot of these kinds of tasks, we also know that sometimes older adults can do just as well as younger adults on a lot of these kinds of tasks. And so we would talk about compensation, right? So compensation means that even though I might have a decline in my inhibitory control or a decline in my attentional resources or anything like that, what I can do is I can just put in a little extra effort. And if I just put in more effort, I can mask my declines by trying harder, right? How do we know this? Well, one way to do it is to actually look at the brain in this case. So what we can do is we can see through imaging like functional MRI or maybe FNIRS, functional near infrared spectroscopy. We can find that oftentimes older adults will show, as I note here, more frontal lobe activity compared to younger adults. Whereas younger adults are showing maybe more activity in the posterior parietal cortex back here. This is part of what's usually thought of as the attentional part of the brain that's more about task positive kinds of situations here, right? You're processing visual information, you're processing body information, spatial information, all things relevant to a task, right? And we see that that starts to decline, but then it is made up for or compensated for by a corresponding increase in prefrontal areas of activation, suggesting here that even though there might be a decline in those sensory regions of the brain, um, by putting in a little more executive control, executive function, which is associated with the prefrontal cortex, then we see this kind of compensation. Um, but one of the things that we're going to see here is that even when older adults show this kind of compensatory activity, that gives them the ability to perform at the level of younger adults, that becomes harder to maintain, right? So it's harder to keep that compensatory activity at the same level. So eventually it does fatigue. And so that means that in a way, older adults are just working harder, right? So they can work harder cognitively and still achieve a high level of performance, but it's harder to maintain that, right? Okay. Um, Next up here is I mentioned the concept of restoration a couple of times. So this idea of depleting attentional resources and restoring them gives us some hints as to what we might be able to do to improve cognition, whether it's in younger adults who are already fatigued and distracted, or whether it's older adults who are showing age-related declines here. First question is nature exposure. Lots of provocative studies have come out over the last few years showing that when we have people do something like a vigilance task, so we can induce fatigue in the laboratory, cognitive fatigue, you're mentally just tired, your attentional resources are declining, and so forth. We can expose them to a nature environment, trees, right? Nature. Or we can put them in an urban environment as well. And what we find is that when you are exposed to natural environments, we see a high level of cognitive restoration. So we bring them back to the lab, put them through the vigilance test again, and now their performance goes up really high. On the other hand, if they're in the urban environment during their break from the tasks, uh, that they don't really restore quite as effectively. So this would suggest that maybe one of the things that we can do here to improve our cognitions is to try to be in nature as much as possible, or take breaks in nature in a green space of some sort, right? I do have a note here that the effects are mixed. So what does that mean? That there's been a number of studies here that sometimes they just fail to replicate them. Sometimes it works if you're actually in a real nature environment. Other researchers have tried to use pictures of nature because not everyone has equal access to green spaces. The effects of pictures then is much weaker and much harder to replicate. But one limitation to this whole enterprise is that even though we might suggest that when an older adult or anyone who is experiencing cognitive fatigue can get themselves into some nature that can restore them, but these are temporary and transient kinds of findings. Since we're asking about aging and aging related declines, we might ask a slightly bigger question, which is there a possibility that a person who has lifelong exposure to nature, to living in an environment that's got easy access to green spaces, do they show less cognitive decline as they get older, right? That's a bigger question. And the answer could be yes, right? So these are called epidemiological studies, right? It's like part of disease studies. If we want to understand what predicts heart disease, we have to like study people over time, check their histories, and look to see, what are some of the commonalities between people who develop heart disease versus people who don't. These are things like longitudinal studies and prospective studies, right? But we can do the same kind of epidemiological research on cognitive decline, and we can look at some variables that connect the dots between people who show very little decline versus people who show more pronounced decline. And there is a growing body of research that suggests that people who have higher residential green space, a little less cognitive decline here. Um, and I mentioned that here for just general cognitive performance, like in a lot of these kinds of cognitive tests that we've gone through in these notes. But also that second study, the prospective cohort study here, also lists all-cause dementia. So that means we're looking at pathological conditions like Alzheimer's disease in this study as well. Another question we might ask is, what about games? And so the question here is, you may have heard of these things, you might have seen ads for them, brain training games and games designed to improve your brain age, right? What is all that? Well, let's ask about it. Actually, this is not anything necessarily new. Video games are relatively recent, but people have been playing games, humans have been playing games for thousands of years. But it's been very common over the last few decades for older adults to prefer to do things like crossword puzzles and other similar kinds of things, like maybe a Sudoku puzzle or something like that, under the assumption that these are good for their minds, right? That they're going to help keep their minds sharp and everything and prevent any decline. A lot of this was inspired by observations that people who have challenging careers cognitively, who use their minds at work, generally show fewer age-related declines in cognition. So this idea of continuously using your mind for things. It's like the old idea of your brain is a muscle, so you better exercise it. And so I need to find ways to continue to use my mind. And maybe these kinds of cognitively stimulating activities like crossword puzzles and Sudoku puzzles could have this effect. Well, as it turns out, the effects are actually not very compelling. That is, we don't really see that when you look at studies of older adults who are active with these kinds of puzzle games and those who are not, and you run them through the kinds of laboratory cognitive measures that we've talked about, we don't see huge differences here. So one thing that is important, I should note here, is that the people who are actively engaged with these puzzles oftentimes have more confidence in their abilities, even if they are not necessarily stronger than the other people who don't do those puzzles. But confidence can be useful here because one of the things we're going to need to talk about, this will be later in the course, is the issue of age-related adaptation to change. How do we deal with and how do we cope with some of the declines in our abilities as we get older? And of importance here is simply just not giving up, right? Not just convincing myself that I can't do anything anymore and I better stop. So we want people to maintain some degree of confidence in their own abilities. But what about these new video games, the so-called brain training games that I mentioned are making these bold claims to improve your brain age, to maybe uh, youthen your brain. Well, they don't work. Long story short, right? They actually have a tiny bit of effectiveness here. But some of the studies, for example, will compare people who play these brain training games to people who are doing other things like reading or watching educational videos, basically anything that requires just a little bit of cognitive stimulation. And what we find is that there's no extra gain coming from the video game. So, okay, video games might do something that's a little stimulating, but there's lots of things that are a little bit cognitively stimulating, and they all basically have the same effects, which is that it is mildly effective, right? And so we'll emphasize mildly effective here. You might notice that in one of our early video discussions for the class, we have a talk from Art Kramer, who spent some time really debunking the effectiveness of a lot of the video game stuff, and largely he is correct. We're going to talk more about his research in the next set of notes because he does a lot of memory research, and so that's the next chapter here. There is one video game thing we can look at here, though. This was a study that came out in the journal Nature a few years ago called NeuroRacer. And what we see is here in this image is that people were given one of three different tasks to perform. Two of the tasks are single tasks where you're only doing one thing. The other one is a multitask or a divided task, right? Drive only is just what it looks like. You are playing a driving video game, essentially, just steering the car down the road. The sign only task is a reaction time task where you've got to keep your eyes fixated on that little green cross. There's a little oval window at the top. Every now and then that green dot will randomly appear. Your task is to press a button. So it's a reaction time task. You have to just, again, fixate the green cross. Whenever that dot happens to flash above, press a button. Sign and drive is we combine both of these tasks, right? You're driving the car, but you're also keeping your eyes fixed at that little cross that sits just above the car, and then monitoring for that occasional green dot. Press the button while steering. You're dual tasking at this point, right? So what they find here is that they trained people on this, right? So they have people performing this task over the course of a month so that they're practicing and they're getting better and better and better. And what we find is that through some brain measurements here, so we look at some EEG and some MRI, especially, we're going to get enhanced activity in the frontal lobe of the brain, which are these executive functioning, right? That's where inhibitory control is happening and all that sort of stuff. And also when we give them other measures of cognition, like, again, sustained attention tasks and working memory tasks, they got better on those too. But importantly, it's only for the one on the right, that sign and drive task. That's the only one that generated this effect. So when the task is kind of simplistic and just one single thing at a time, we're not going to see this kind of transfer of training. But when it is more of a multitasking situation, this long-term practice on this seems to improve overall kind of attentional performance a little bit. So promising signs from the NeuroRacer study here as well. Uh, all right, that is the end of that note. So I will go ahead and call it on this video and see you next time.